Wednesday, April 16, 2025, possesses the profound potential to be enshrined in human history as the pivotal moment the ancient and haunting mystery of extraterrestrial life was finally solved. On that day, the scientific world and the public at large were electrified by a report from News Vogue, citing a groundbreaking publication in the astrophysical journal Letters, which revealed that a dedicated team of astronomers at the University of Cambridge had uncovered something truly astounding. Their discovery centered on a distant world, a planet orbiting a star a staggering 124 light-years from Earth, that may very well support alien life. This planet, known as K2-18b, if the initial interpretations of the Cambridge team hold true, was found to possess an atmosphere showcasing what can only be described as a gigantic biosignature. This finding stands, undeniably, as the strongest evidence for life on an alien planet that humanity has ever encountered. Of course, the researchers involved have been meticulously careful to emphasize the critical distinction between evidence and proof. We cannot yet jump to conclusions. However, by virtue of the sheer weight and implication of their discoveries, this team has unequivocally brought our species closer than ever before to solving the ultimate cosmic mystery. To understand the magnitude of this announcement, one must delve into the nature of the planet itself, the painstaking science behind the discovery, the sobering cautions that temper the excitement, and the thrilling path that lies ahead. The planet K2-18b is, in many respects, remarkably unremarkable within the ever-growing catalogue of known exoplanets. It orbits a red dwarf star called K2-18, located at a distance of 124 light-years from our solar system, a vast gulf of space where a single light-year, a measure of distance, represents about 6 trillion miles or 9 trillion kilometers. K2-18b is classified as a sub-Neptune, meaning its radius is smaller than that of the Neptune we know in our own cosmic neighborhood. Specifically, it measures about 2.5 times the radius of Earth and possesses a mass roughly 8.5 times greater than our planet's. Its most enticing feature is its location, sitting comfortably within the habitable zone of its host star, that Goldilocks region where conditions might be just right for liquid water to exist on a planet's surface. Early estimates placed its average surface temperatures between -13 and -3 degrees Celsius, 8 to 27 degrees Fahrenheit, suggesting that while some regions could be hospitable, most of its water would likely be frozen. However, as with Earth, averages can be deceptive, and warmer regions could certainly exist. K2-18b completes a full orbit around its Sun every 33 days and was first identified by the Kepler Space Telescope in 2015. It shares its solar system with at least one other planet, a smaller, gas-rich neighbor, and the two may be close enough to exert significant gravitational influence on one another. Furthermore, it is believed to be tidally locked to its star, meaning one side perpetually faces the light while the other is shrouded in eternal darkness, though this has not been confirmed. Despite its seemingly typical profile, K2-18b has captivated the planet-hunting community for years. The first major breakthrough came in 2019 when astronomers confirmed the presence of water vapor in its atmosphere, a landmark discovery as it was among the first of a smaller, potentially rocky exoplanet, as opposed to uninhabitable gas giants, to exhibit this trait. This finding placed it under intense and continuous scrutiny. Subsequent studies began to overturn initial assumptions about its climate. Researchers proposed that a chilly outer atmosphere might be masking a much warmer, heat-trapping environment below, with some models suggesting a hidden surface could reach a scorching 200 degrees Celsius, nearly 400 degrees Fahrenheit. This led to its classification as a potential Hycean planet, a theoretical world with a hydrogen-rich atmosphere and a vast global ocean of liquid water beneath. This concept was revolutionary because such planets had previously been written off as uninhabitable, presumed to suffer from a crushing greenhouse effect similar to Venus. K2-18b defiantly challenged that assumption. The intrigue deepened in 2023 when the same Cambridge team, led by Professor Nikku Madhusudhan, detected both carbon dioxide and methane in the atmosphere, key chemicals often associated with biological processes, with CO2 levels about 25 times more abundant than on Earth. These findings already cemented K2-18b's status as a premier candidate in the search for life. But the data released in April 2025 catapulted it from an interesting contender to the absolute forefront of astrobiological study. The monumental breakthrough was the result of a sophisticated analysis of the exoplanet's atmospheric chemical composition using data from the James Webb Space Telescope, JWST. The analysis revealed the presence of two exceptionally important molecules, dimethyl sulfide, DMS, and dimethyl disulfide, DMDS. On Earth, these compounds are profoundly significant. While they can be synthesized in laboratories by humans, they are only known to occur naturally as byproducts of biological activity. Specifically, the only natural source of dimethyl sulfide known to our planet is marine phytoplankton, microscopic algae that form the base of the aquatic food web. Their presence in an alien atmosphere is, from an Earth-centric perspective, the clearest possible telltale sign, a screaming biosignature, that where these compounds exist, life is also likely to be found. Moreover, the specific type of biosignature hints at the possible nature of that life. The detection of DMS and DMDS suggests that if Earth's biosphere is any guide, K2-18b might host vast, teeming oceans filled with microorganisms analogous to our own phytoplankton. The implications are staggering. We may be looking at a world whose fundamental biological processes mirror those on our own planet. The credit for this discovery belongs to the relentless work of Professor Madhusudhan and his team of 6 researchers at the University of Cambridge's Institute of Astronomy. Their work is a testament to scientific perseverance, building directly upon their own earlier observations from 2023. Even then, their data contained faint, tantalizing hints of a DMS signal, putting them on the trail of a biological marker with potentially universe-altering implications. The most recent study, using the unparalleled power of the JWST, which orbits the Sun 1 million miles from Earth, has now confirmed the identification of DMS at a statistical confidence level known as 3 sigma. This means there is only a 0.3% probability that the detected signal is merely random noise or a fluke. The team estimates that just another 16 to 24 hours of dedicated observation time with the JWST would allow them to reach the gold standard in scientific discovery, the 5 sigma confidence level. This would reduce the chance of error to a minuscule 1 in a million probability, meeting the formal standard for a confirmed discovery. As Professor Madhusudhan told the BBC, "This is the strongest evidence yet that there is possibly life out there. I can realistically say that we can confirm this signal within 1 to 2 years." He added a profound corollary: confirming life on K2-18b would fundamentally suggest that life is very common throughout the galaxy. His reasoning is sound. K2-18b itself is utterly unremarkable, a common type of planet, a sub-Neptune, orbiting a common type of star, a red dwarf, in a common location, the habitable zone. If life emerged so easily on such a common world, the universe may be overflowing with it. This apparent ease of discovery is itself a profound point. The dedicated search for life on exoplanets has been ongoing for decades, yet we are still in the infancy of this endeavor. The JWST is the first and only telescope capable of performing this precise type of atmospheric spectroscopy on distant exoplanets, and it has been operational for only a few years. The fact that it may have pinpointed a nearby ocean world teeming with life so early in its mission suggests that such life-bearing worlds might not be rare anomalies but could instead be entirely common. Yet, amidst this breathtaking potential, the Cambridge team has been a model of scientific integrity and transparency, repeatedly cautioning that it is far too early to draw any definitive conclusions. This caution exists for several compelling reasons. First, even if they achieve the coveted 5 sigma confidence level, it would only irrefutably confirm the asterisk presence of the gases asterisk in the atmosphere. It would not, and cannot, confirm that those gases are definitively produced by biological processes. That interpretation remains, for now, well-informed and thrilling speculation. The scientific community must relentlessly pursue alternative, non-biological explanations for these compounds. We know that DMS can be manufactured artificially. Laboratory experiments have shown it can form when ultraviolet light interacts with certain chemical soups in planetary atmospheres. It has also been detected on comets and within interstellar gas clouds, environments utterly hostile to life as we know it. The Cambridge team has already argued that neither comet delivery nor UV-driven atmospheric chemistry could account for the massive quantities of DMS they observed, but the broader point remains: our knowledge is limited. Other, as yet unknown geological or chemical processes. Furthermore, there is still active debate within the scientific community about the very nature of K2-18b. While the Cambridge team models it as a Hycean world, other studies have proposed radically different and far less hospitable models, suggesting it could be a world covered in a global magma ocean or even a predominantly gaseous mini-Neptune without a solid surface at all. Our current tools for studying objects 124 light-years away are still imperfect, leaving ample room for reinterpretation. However, if the biological interpretation is correct, the implications are mind-boggling. Molecules like DMS break down quickly in atmospheres. Therefore, their persistent presence cannot be a one-off event, like delivery by a single comet impact. There must be a continuous, ongoing source replenishing them. This implies that if the source is biological, K2-18b would have to be absolutely teeming with life, its oceans so densely packed with algal blooms that they resemble a planet-wide version of an earthly pond choked with green organic matter, constantly venting these gases into the air. So, what comes next? The immediate path is one of meticulous, patient science. The first step is for the Cambridge team to secure more JWST observation time to solidify their signal to the 5 sigma level. Once achieved, the presence of these biosignature gases will be considered an established fact, shifting the debate from if they are there to why they are there. Equally important will be the work of independent teams across the globe who will now train their own telescopes and analytical prowess on K2-18b, seeking to validate, replicate, or challenge the findings. This process of external review and replication is the bedrock of the scientific method. In parallel, the community will engage in a process of disconfirmation, actively and aggressively seeking every possible alternative explanation for the data that does not involve alien life. This is not a cynical exercise but a necessary one to strengthen the findings. As the Cambridge team stated, it's important that we're deeply skeptical of our own results because it's only by testing and testing again that we will be able to reach the point where we're confident in them. That's how science has to work. Sending a probe is not a viable option, even at the incredible speed of the Parker Solar Probe. A journey to K2-18b would take over 115,000 years. For the foreseeable future, we are limited to remote observation. We will not be able to determine if single-celled organisms on K2-18b have evolved into more complex forms. Our tools are simply not yet that powerful. For now, humanity enters a period of anxious and hopeful waiting. Within a few years, further observations may reveal that the signals were misinterpreted, and K2-18b may become a footnote in history, a cautionary tale about premature excitement. Or, in that same near future, the evidence may become so overwhelming that we will find ourselves living in a new, paradigm-shattering reality, a universe where we are not alone. In that transformative moment, the ancient human dream of a living, teeming, abundant cosmos will have finally transitioned from the realm of imagination into tangible, scientific fact. The announcement of April 16, 2025, therefore, is not an end, but a spectacular beginning, the opening of a new chapter in our understanding of our place in the universe. Thank you for watching.